Okay, in the last couple of sections, we talked about bonds between atoms that form molecules. In this unit, we're going to talk about intermolecular bonds or bonds between molecules. These are also known as hydrogen bonds. So, when we have a molecule that uses polar covalent bonds, these make what we call polar molecules. Water is probably the most important of these. So, in water, we have an oxygen bonded to two hydrogens. And because the oxygen is bigger than the hydrogens, it has more positive charge because of the more protons. That means the electrons like to spend more time here. So, this end of the water molecule becomes partially negative. The hydrogen ends of the water molecule therefore become partially positive because they don't see the electrons as often. Now, what this means is that when you have more than one water molecule, the partially positive end of one water molecule will be attracted to the partially negative end of another water molecule. And same thing between this molecule and another water molecule. The partially positive attracted to the partially negative. Each one of these is an individual distinct molecule, and these are not permanent bonds. These are called hydrogen bonds because the partially positive end of the molecule is always one of those puny, weak hydrogens. Depending on what molecule we're looking at with hydrogen bonds, this may be oxygen, this may be something else, but there's always a hydrogen involved, so we call it a hydrogen bond. And hydrogen bonds are represented by dotted lines because that is supposed to indicate that they are not as strong as covalent bonds. Okay, hydrogen bonds are why when you pour a glass of water, you can actually pour more water in the glass than the glass actually holds. Basically, the water molecules up here are holding on to each other with those weak bonds so that when the water molecules should be spilling over, their buddies that are still in the glass are holding on to them, pulling them in. Of course, this doesn't work forever. You can't pour the water like an inch above the glass. But as long as you are not too far over the glass, the hydrogen bonds between water molecules hold it together. We call this surface tension. And surface tension is going to play an important role in several physiological processes that we learn about in A&P. Now, because water is polar, it can easily break ionic bonds. Remember, we saw an ionic bond between sodium and chloride. So when they're sitting at the bar and they're not in the swimming pool full of water, sodium and chloride are super attracted to each other. You really have a hard time getting them apart. But as soon as you put them in water, sodium and chloride become separated. And this is because the positively charged sodium can be surrounded by a bunch of water molecules, and they're all pointing their negative end towards the sodium. So sodium's like, okay, well, I kind of miss chloride, but you guys are making me feel better by giving me all that negative charge that I'm attracted to. And same thing with chloride. Chloride is negative, and the water molecules surround it, pointing their positive ends towards the chloride. So chloride is feeling a little comforted that it doesn't have its new lover, sodium, nearby. Allows us to separate the ions, which, when we get to things like nerve and muscle and membrane transport, this is super important that we're able to separate the two electrolytes, the two ions, and treat them differently. So, in summary, and I'm not sure they'll put me up here, so I'm out of the way. We saw ionic bonds, which is one atom gives its electron away completely to another atom, and they each become charged and then they become attracted to each other. We saw nonpolar covalent bonds when two atoms share an electron from their valence shell and they share it equally. And then we saw polar covalent bonds when two atoms share their electrons in their valence shell, but they don't share them equally, and the electrons spend more time around the larger of the two atoms. And then, because we created polar molecules, we saw hydrogen bonds form between the different polar molecules. Now, hydrogen bonds are the weakest of all of these, but when you add all of the hydrogen bonds together in, say, a container of water, it's enough to hold the water in the glass. And we're going to see the same thing at play when we look at how two strands of a DNA molecule are held together by hydrogen bonds. Each one is weak individually, but if you look at the whole of the molecule, it's strong enough to hold the strands together. And same thing with protein folding. All right.